Okay, so we'll start our talk. We are very happy to be here again in Sweden, Stockholm, Sekti, the land of Vikings and IKEA. And today we will present how we found many vulnerabilities in third-party drivers in Linux in a colorful way. I'm Eran Shimony, a security researcher at CyberArk, primarily focusing on the discovery and exploitation of local privilege escalation bugs across VIA operating systems. And I really enjoy also drinking and mixing cocktails, and sometimes doing meditation can happen on the same time.
Hello everyone, my name is Tal Lossos and I'm a vulnerability researcher at CyberArk Labs, focusing mainly on operating system internals, and except playing with kernels, I'm enjoying CrossFit.
So let's see what we have on our menu today. We will start with the difference between a research in open source versus closed source. After that, we will have some Linux kernel internals 101, enough for us to understand the bugs, but not too much to make you fall asleep. After that, we will go to a very important piece in every privilege escalation research, to which privilege part can I talk from the unprivileged. Later, we will see how messing up with the colors on your keyboards can affect to bugs. And lastly, we will examine a new mitigation in the Linux kernel that greatly reduces the severity of buffer overflow attacks from the potential of privilege escalation to a mere denial of service. So let's start. Closed source versus open source. On the right, we have the beautiful penguin indicating the lovely operating system of Linux. And on the left, we have the not-so-lovely broken window indicating the operating system of Windows. So those are the two operating systems we will talk about. We can also honorably mention Mac, which is kind of in between open source and a closed source, because you can argue this new kernel is open source, but the rest is closed source. So what is so special about closed source? Well, obviously, we lack the code of it. So in order to understand what happens under the hood, we either need to execute it, which really doesn't add anything when we talk about drivers, or reverse engineer the hell of it. Now, in order to reverse engineer and understand what happens, we need to have strong knowledge of low-level operating system, and have the ability to have, to exploit things, which is a very tiresome action, and it takes time. The good and the plus about it is that usually those tend to be harder to exploit, so vendors pay nicer bug bounties as a reward compared to open source projects. The approach we are going forward in this type of research is first, we try to gather every possible intel over our target. If, for instance, we try to find a bug in the Windows kernel grapher, Win32k-sys, that consists of several thousand functions, it will be impractical to start with just reversing the binary. So every blog piece or talk about it is greatly beneficial for the task. Later, we will try to find any possible code leaks. Now, every version of the Windows kernel had code leaks in its history. And doing a patch diff between a decompiled or disassembled output to the source code, even though if it could be a bit dated, is very helpful than just having nothing. After that, it's very important to define our target very closely, because it's very easy to get spread away while doing research. Like if you reverse engineer, you're familiar that we start with one function, and one function leads to 100 functions. And it's very important for us to have a straight line at our target. So the way we do it is mostly via reversing and also via fuzzing, but we will touch about fuzzing soon. And open source, on the other hand, of course, we have the source code. We can understand anything that actually happens. Besides that, we can use the tools called static analysis in order to find low-hanging fruit bugs and more. And lastly, we can compile and add debugging snippets, instrumentation into the code that will help us in the exploitation phase. Now, the first step, of course, in open source research is to find the damn code via GitHub, Git, or if you use the dark technology called SVN, you can go there, of course. Now, the second step is to run several static analysis tools. Now, those tools are very beneficial because they can help us find memory corruption type of bugs, divide by zero, integer overflow, and underflow in a pretty short time. Additionally, there are some advanced tools like CodeQL that allow you to write advanced queries that treat your code as a database, and then you can really track the data flow from one function to another, which is another great tool. After that, we compile and build the open source, usually adding some debug statements that give us vision about the state of the software in important parts. And lastly, if we manage to actually find a vulnerability in the code base, there are good chances these vulnerabilities can carry the way to other products as well. As you're probably familiar, developers are humans, and humans are a bit lazy, and we copy code from one project to another. So once we find a vulnerability, we can probably find it in different places, and we will see it. And now there is the question of fuzzing. If you're not familiar, fuzzing usually consists of generating input towards a target function with some kind of feedback mechanism that tracks the code coverage. Code coverage basically is the amount of paths you went into the target software. Sounds fantastic. Well, one of the problems that it takes time. Everyone who used Fuzzer, let it be AFL, libfuzzer, or syscaller, is familiar with the thing that it takes time to customize the fuzzer to your own solution. One approach that is kind of in the middle, and the one that we used in this research, is the usage of a dumb fuzzer. A dumb fuzzer does not have any fancy feedback mechanism. It just tries many input that we have some prior knowledge about the software beforehand. And it's very useful in the case we know the specifics of the target. For instance, we know we need to go to a particular function, and we don't need really to spread out in the entire code base. And of course, if you have more time, several weeks or months, you can use a full-blown fuzzer. And in some cases, the more advanced project, you need to use a better fuzzer. So what are the main takeaways of open source research and why it's a bit easier? We have endless examples that we can learn from. People in the community are usually very supportive, so we can ask them about them. People tend to focus less on open source, so there are more low-hanging fruits. And those low-hanging fruits bug can be impactful as a very difficult bug. It really doesn't matter. You have the option to add code into the code base and compile it, of course, making debugging life a lot easier. Fuzzing is also easier because most of the fuzzing revolves around instrumentation, and it's pretty out of the box if you can debug the program with adding code. And lastly, reverse engineering is also easier because if you have the source code and you have the decompiled output, and if the compiler puts some shenanigans inside of it, you can pretty much easily understand what has been done. So maybe if you were here last year, you remember that we gave a talk about how to find bugs in Windows drivers and third parties using KFL. But today we are not going to talk about Windows. We are going to talk about a specific penguin.
Yeah, so as you maybe have figured out, the penguin in the room is the Linux kernel, or more specifically, Linux kernel modules. But to understand what Linux kernel modules are, let's first understand the general architecture of the Linux operating system. So most of the operating system are divided into two mainly parts, the user space and the kernel space. The main difference between them is that the kernel space is the actually privileged part of the operation system that can interact with the hardware. An example of that could be when the user requests to read a file from a disk. The request actually goes through the kernel, which then proceeds to read the data from the disk and returns back to the user space. When installing an operating system like Ubuntu, you will get the kernel obviously installed with it. So if you're installing Ubuntu, for example, you will get the Linux kernel installed with it. But it doesn't mean that you cannot update or cannot add functionality to the kernel in runtime. Adding functionality in kernel runtime, it's done via kernel modules. For example, you can add new hardware devices supports, new kernel devices, new keyboard devices, USB, and everything that uses the hardware most likely will require a driver to know how to interact with it. So we've conducted our research focusing on the Linux kernel because essentially each bug in the kernel is critical due to the fact that the kernel is always privileged. And one of the best places to hunt for bugs in kernel are third-party kernel modules, because most of the time they're less examined and are accessible by restricted user. Exploiting kernel modules bug can lead to the same impact as exploiting vulnerabilities in the kernel itself. So it can be exploited to a denial of service or to a full local privilege escalation, for example. The way we've done it is by looking for big third-party vendors and examining their code, which one of them was Razer. So if you may know, Razer is a big peripheral hardware vendor focusing mainly on gaming gear. And if you want to interact with them in a Linux environment, you will most likely use the Open Razer software, which is open sourced. So it lets you to customize your hardware. So for example, it lets you to create custom macros for your keyboard, custom RGB. It even lets you to customize RGB colors for your mag holder, for example, which is amazing. And again, it lets you to set different DPI and every configuration that you may think about. Every type of hardware device that you can see here translates to an additional driver that you have to load into the kernel to interact with it, which expands greatly our attack surface. An example of what you can do with the Open Razer will be, for example, the great Swedish flag. One of the prime things that we need to understand while conducting a vulnerability research is how we can communicate between the not privileged and the privileged part. And in our case, how we can transfer data between the user space and the kernel space. In Linux, there are multiple ways to do it, which we'll go briefly over the main ones. So first of all, kernel modules can implement the normal read and write operation, which then can be accessed on an exposed file via the read or write syscalls. Otherwise, the kernel module can implement the ioctl API interface, which usually each functionality is distinguished by the command parameter. This way is very nice to use when using a non-generic functionality. So basically everything besides reading and just writing normal data to the device. Another way to do it is by using shared memory between the users and the kernel space. By doing this, it will be the fastest way of communication between the user and the kernel. Linux also allows you to use exposed file on a virtual file system like sysfs, for example. This way is very nice to use because most of the time, each functionality will be exposed on a different file via this file system. And it's really nice to use it when you want to interact with your kernel modules via shell scripts, because again, interacting and just writing and reading to files is very easy. And lastly, there's another way I wanted to mention, which is using the netlink socket. This is a really nice way if you don't want to just use files. It's just creating a netlink type socket in the kernel, and then it can be using like normal socket communication via the user space. So how can we even communicate with our devices? So if we will use Linux, so first of all, we need to make sure that the kernel modules are indeed loaded into the kernel. This can be done by running lsmod. lsmod shows us all the kernel modules that are loaded into the kernel, and grabbing Razer will show us the drivers. Because Open Razer chose the VFS type of file functionality exposed, we need to know what's the path of the exposed file. So to know that, we need to make sure that we know what's the vendor ID and what's the product ID of the device. This can be done by running lsusb. Just have a note that Razer's vendor ID will be always hexa1532. And by running lsusb, it will show us all the connected devices via USB, and we can know that's the product ID. And lastly, we can read or write into the exposed file. For example, if we're echoing 1, which is just writing 1, into the file called matrix effect wave, it will trigger the implemented functionality in the kernel module, which is supposed to lastly use the wave effect on the device. So it will do this. And we can see it also here. All right, so now that we know how we can interact with the kernel modules, let's go to the fun part of hunting bugs.
Thank you. So what are we after? We're after memory corruption type of bugs, and more specifically, null pointer dereference, arbitrary pointer dereference, any kind of pointer dereferences, buffer underflow, and the classical familiar buffer overflow. Now, the potential places that we aim to find them is that of copying data from one way to another, like in memcopy, strcopy, and so on. and while doing the reference operation without doing proper checks about the pointer values beforehand. And let's introduce two very actually famous terms, source and sinks. So on the left, we have Nikola Tesla, the inventor of the light bulb. Without him, there wouldn't be probably RGB colors, and we wouldn't be here.
Thank you.
So props for him. Thank you. And on the right, we have a sink with blue color and so on. So the two approaches that we use in order to find vulnerabilities is either go from the source to the target or from the target to the source. In other words, we first map where we can enter, where our payload from the user enters to the kernel, and then where the target is, for instance, a vulnerable mem copy operation. After that, we do the other way around. From the mem copy operation, we trace the path into the source. In other words, first we ask ourselves to which function do we have access to from unprivileged user. Next, we try to determine which arguments we have control over and what affects them. Then we will look for data copying operations like the memcopy, strcopy, and pointer dereferences. Any one of those operations is a good place to look for a bug. And then what we do backward tracing. We're going back from the sink to the source. So we, again, look for all the vulnerable operation. We see how the arguments in between are changed, and then we determine if the function is even accessible. While doing those two things, we are like grasping a stick in two hands and going into the middle, allowing us to have better understanding if there is a vulnerability here that we can exploit from a non-privileged user. So let's have an example. This is like a real example in one of Razer kernel modules. The function is called Razer comma extended matrix set custom frame 2, and it's responsible to change the lights of your keyboard. You can see that it receives an argument called war index, the row of your keyboard, start column, and stop column. Also, it receives RGB data, which is the color of the thing you want to change on your keyboard. Can you maybe spot a vulnerability here? So a good place to look is the memcopy instruction. And we also need to know that, I didn't tell you that the report argument buffer is in the length of 80 bytes. Now, there is the third parameter of the memcopy instruction, the row length. And the row length is being calculated in stop column plus 1 minus start column times 3. And you're probably familiar that the max size of unsigned car is 255 bytes, 2 to the power of 8 minus 1. And while multiply it by 3, we get the value of 765. Now, the way the memcopy instruction works is that you copy the first 80 bytes into the buffer, and then we have a roughly 685 bytes of overflow on the stack, the very classic stack overflow bug. Now, that in itself is not enough like to escalate into root or to run code in the kernel, but alongside another primitive of an infoleak, for instance, is enough to pass every mitigation. So we thought, but short about that. Now, another vulnerable code, as we said earlier, one code can carry the way to another project. This is the Razer report, Razer comma misc1 row set custom frame function, and it suffers from the same bug. And this lovely function is responsible for this very important device. So by having this mug holder, it makes you vulnerable to denial of service attack and privilege escalation ones in the kernel. So this metal fin can be hot, it can be cold, and it's most definitely vulnerable to code. And lastly, another place we found the same vulnerability in Razer Chroma standard matrix set custom frame is for your mouse, to change the colors of your mouse. So the message here is, don't connect things to your computer with cool colors. I don't know. Now let's see a demo showing case that. So the first thing we do, as we seen earlier, is running LSU USB. LSU USB. And we can see here that we have the vendor ID and the product ID of Razer. Let's run ls mode to see if it's indeed loaded in memory. We can see we have the Razer accessory here. Now, let's present our payload. It's a very simple payload. We can see here that we must have the vendor ID, the product ID. The target function that we send the payload into is matrix custom frame, which is responsible to light this nice thing. We can see our buffer is longer than 80 bytes, and hopefully, if everything works, we will crush the kernel. So let's try the moment of truth. No, let's see what happened.
I know. Okay, 1 sec, please.
Every time we reboot the machine, we need to change the number of the device. And now, hopefully, anything will work. Yeah. OK, and we crash the kernel. And we are very happy about that.
All right, so during the exploit development, we encountered a newly added feature into the Linux kernel, which was a part of Fortify source mitigation. Fortify source basically aims to detect buffer overflows in compilation time and to mitigate them in runtime. An example of runtime mitigation could be when using a memcopy operation with a dynamic size. The Fortify source originally came from glibc, but got introduced into the Linux kernel into multiple steps. Which we'll call them mods, which introduce 2 mods, which we'll call them mod 0 and mod 1. Mode 0 aims to detect buffer overflow over an entire struct, and mode 1 aims to detect buffer overflows even in specific members on a struct. Let's have an example. Let's assume that we have this object struct, which has 3 members. arg1, which is in size of 2 bytes, an array in the size of 6 bytes, and another member called arg2 in the size of 4 bytes, followed by a memcopy operation on the R buffer. If we compile our kernel module with Fortify source enabled in mode 0, we can indeed still overflow our buffer, thus overriding the data stored in arg2. But if we run in Fortify source with mode 1, we cannot overflow the arg2, thus much safer. So let's see the example in our code. I'm showing the disassemble code because, again, this mitigation is inserted in compilation time. This is our vulnerable memcopy operation without Fortify source enabled. As you can see, there's no any validation on row length. Thus, we can easily, as you saw, crush. But if we compile the kernel module with Fortify source enabled, we can see that a check was added, that checking if indeed our row length is bigger than the allowed copy size into the buffer, which here will be 0x4d. And if indeed the size will be bigger than the value, we will call Fortify panic, which will crush more safely the driver. Just have a note. OK, let's see the Fortify source history. So Fortify source mitigations first introduced in the Linux kernel in kernel version 4.13, where mode 0, again, for just checking an entire struct, got introduced for both strcopy and memcopy family of function. Later on kernel version 5.11, mod 1 got introduced for strcopy family of function, but still mod 0 was turned on for memcopy family of function. Very recently, in kernel version 5.18, mod 1 was turned on for both of them, but still the memcopy only had the compile time mitigation. So the runtime mitigation was still not enabled, and last week, the runtime mitigation for mod 1 for memcopy got introduced. Again, this mitigation only exists currently in the Linux, but again, for older version that you see here, exploiting buffer overflows in the kernel can still be exploited into everything beyond denial of service. All right, after finding the vulnerabilities, we reported them to the open source project with a fixing PR, which was merged and released on the same day. Multiple CVEs were assigned to the vulnerabilities, and we have a couple more under disclosure. and a blog post about this topic that goes more deeply into the vulnerabilities and the 45 source mitigation just published today. So go check it out in CyberArk Labs site. You may ask yourself, what's next? So last year we've covered Windows, this year we're covering Linux, and maybe next year we'll cover a more Apple-ish operating system or more pinkish. We don't know yet. Thank you. Feel free to ask any questions.
Please. Sorry? How does it interact with our vulnerability? Well, the kernel module is loaded. You have the open functions that you can send actually the payload into that change the color of the mug, for instance, or the keyboard, and that's it. It's like calling a function.
Any more questions from the audience? Okay, then thank you very much for the presentation. Thank you.